This is 2 full hours of complete calculus, the whole story from the very first time a human tried to measure something curved, all the way to the mathematics running inside the phone on your nightstand right now. So settle in, get comfortable, pull the covers up if you need to. This is not a class. There is no test tomorrow. There is nothing you need to remember, nothing you need to write down. This is just a story about one of the most beautiful ideas anyone ever had. And I want to start by saying something about calculus that I think really matters. Somewhere along the way, we started teaching this subject by throwing definitions at people. Here is a limit, here is epsilon delta. Memorize this formula, differentiate that. And if you ever sat in a classroom and felt like calculus was designed to make you feel stupid, that was not your fault. That was a failure of storytelling. Because the people who actually invented calculus, the people who spent their lives wrestling with these ideas, they did not start with definitions. They started with a question, a very simple, very human question. How do you measure something that will not hold still? That is what calculus is, at its heart. Underneath all the notation and the formulas and the rules you were asked to memorize, it is the mathematics of things that change, the mathematics of motion, of growth, of anything that flows or curves or refuses to sit still. And the story of how we figured it out stretches back thousands of years, across every major civilization on Earth, through some of the most dramatic and fascinating lives in the history of science. Tonight, we are going to walk through all of it, the whole thing, from the very beginning, nice and slow, no rush, nowhere to be. So let us start at the beginning. And the beginning is much, much older than most people realize, around 1820 years before the Common Era. So, roughly 4,000 years ago, someone in Egypt sat down and wrote on a piece of papyrus. We do not know their name. We do not know if they were old or young, a teacher or a student, working alone or surrounded by others. What we do know is what they wrote, because that papyrus survived. It is called the Moscow Mathematical Papyrus, and it is sitting right now in a museum in Russia, which is a whole other story of how artifacts travel through time and across continents in ways their creators could never have imagined. On that papyrus, among a collection of mathematical problems, there is one that stops modern mathematicians in their tracks. It is a formula for the volume of a frustum. A frustum is basically a pyramid with the top sliced off. So you are left with this squat, trapezoidal shape, wider at the bottom, narrower at the top. Think of it like a bucket or a flower pot or one of those little pedestals that statues sit on. And the formula that this anonymous Egyptian scribe wrote down for calculating its volume was correct, not approximately correct, not a rough estimate that gets you in the neighborhood. Correct. The exact formula. Now, here is what makes that remarkable. To derive that formula properly, using the tools of modern mathematics, you need integral calculus. You need to be able to slice that shape into infinitely thin layers, calculate the area of each layer, and add them all up. That is integration. And somehow, 4,000 years ago, Someone in Egypt arrived at the right answer without any of that machinery. How they did it, we honestly do not know. Maybe they built physical models and measured them. Maybe they had some geometric insight that has been lost to time. Maybe they just tried enough specific cases that the pattern became undeniable. Whatever the method, the result is stunning because it means that the instinct behind calculus, the drive to measure curved and irregular things with precision, is almost as old as civilization itself. And they were not alone. Around the same era, across a stretch of desert to the east, the Babylonians were doing something equally extraordinary. Now, the Babylonians are one of those civilizations that I think do not get nearly enough credit in the popular imagination. When most people think of ancient mathematics, they think of Greece, they think of Euclid and Pythagoras and marble columns. But the Babylonians were doing sophisticated mathematics 1,000 years before any of that. They wrote on clay tablets in a script called cuneiform, pressing a wedge-shaped reed into soft clay and then baking it. And because clay, unlike papyrus, is incredibly durable, we actually have thousands of these tablets. They are sitting in museums all over the world, and the mathematics on them is astonishing. The Babylonians had a number system based on 60, which is why we still have 60 seconds in a minute and 60 minutes in an hour, and 360 degrees in a circle. A decision made over 4,000 years ago in Mesopotamia is still shaping how you tell time and measure angles today. But the thing I really want to tell you about is what they were doing with the sky. The Babylonians were obsessed with astronomy. And when I say obsessed, I mean it in the deepest possible way. This was not a casual hobby. Astronomy in ancient Babylon was woven into religion, into politics, into agriculture, into the rhythm of daily life. The movements of the planets were omens. They told you when to plant, when to go to war, when to crown a king. Getting the sky right mattered in ways that are hard for us to fully appreciate today. And they tracked the movements of the planets with a precision that is, frankly, hard to believe given their tools. They had no telescopes. They had no clocks in any modern sense. They had their eyes, their clay tablets, and centuries, literally centuries, of accumulated observations passed down from generation to generation, night after night, year after year, decade after decade. Babylonian astronomers sat in the open air and watched the sky and wrote down what they saw. And over hundreds of years, those records accumulated into something extraordinary, a data set so deep and so detailed that they could predict celestial events with startling accuracy. Now, here is where it connects to calculus. And this is the part that genuinely stops me every time I read about it. Among the tablets that have been found and translated, there are records showing that Babylonian astronomers were tracking the motion of Jupiter across the night sky. Jupiter, as you probably know, does not move at a constant speed from our perspective here on Earth. It speeds up, slows down, and even appears to move backward at certain times of the year in what is called retrograde motion. So, tracking Jupiter is not a simple problem. Its apparent velocity changes over time, and the Babylonians figured out how to deal with that. They recorded Jupiter's velocity at different points in time, and then to calculate how far Jupiter had actually traveled across the sky over a given period, they did something that a modern calculus student would immediately recognize. They drew a graph with time on one axis and velocity on the other. They looked at the area under that curve and they computed it by dividing the shape into trapezoids and adding up their areas. Let me make sure that lands because it is easy to hear that and not fully register what it means. Imagine you want to know how far your car traveled on a road trip, but the only information you have is a record of how fast you were going at every moment. You were doing 50 miles per hour at the start, then 60, then 45, then back up to 70, constantly changing. You cannot just multiply speed times time because the speed was never constant. So what do? You break the trip into tiny intervals. For each little slice of time, you take your speed during that interval and multiply it by the length of the interval. That gives you the distance you covered during that one little slice. Then you add up all the slices, and the more slices you use, and the thinner you make them, the more accurate your total distance becomes. In the limit, when the slices become infinitely thin and infinitely numerous, you get the exact distance that is integration. That is the core idea of one entire half of calculus, and the Babylonians were doing it on clay tablets to track Jupiter. And here is the part that stops you in your tracks. They were not doing this for abstract mathematical beauty. They were not sitting around thinking about the philosophy of infinity or the nature of continuous change. They were doing it because they needed to know where Jupiter would appear in the sky next month. They had a practical problem, a real urgent night sky problem about a wandering point of light, and they invented a technique to solve it, a technique that would not be formally understood, not properly named, not rigorously defined for another 3,000 years. I want you to sit with that for just a moment, because it is genuinely one of the most remarkable things in the entire history of human thought. 4,000 years ago, in Mesopotamia, someone pressed a reed into wet clay and performed what we would now call numerical integration to track a planet on clay tablets. In ancient Mesopotamia, they were doing calculus before the word existed, before the concept had a name, before anyone had any idea that what they were doing was part of something much, much bigger. Now, here is something worth thinking about. Both the Egyptians and the Babylonians achieved these remarkable results, but neither of them did something that might seem like the obvious next step. Neither of them stepped back from their specific solutions and said, wait, there is something deeper going on here. There is a general principle connecting all of these techniques. The Egyptians had their frustum formula. The Babylonians had their trapezoid method for areas under curves. Both of these are, in modern terms, instances of integration, but neither civilization built a general theory of integration. They solved specific, brilliant, individual problems. They did not generalize. And I think there is something important in that, something that tells you about how mathematical ideas actually develop. It is not enough to solve a problem. You also have to recognize that your solution is an example of something universal, and that second step, the step from a clever technique to a general principle, is incredibly hard. It requires a different kind of thinking entirely. It requires you to look at your own work from the outside, to see the pattern behind the pattern, to go from saying, I solved this one problem, to saying, I understand why this solution works, and I can apply it to problems I have not even encountered yet. That leap from the specific to the general, from the practical to the abstract, is arguably the most important leap in all of mathematics. And it is a leap that takes time, sometimes centuries, sometimes millennia. The Egyptians and Babylonians were standing right at the edge of it. They had the raw material, they had the intuition, they just had not yet found the words or the framework to name what they were doing. Think of it like measuring a coastline. If you take a ruler and hold it up against a map, you can get a rough answer, but the more carefully you look, the more detail you find. Every bay has smaller bays inside it. Every peninsula has smaller peninsulas. The closer you zoom in, the more complex the shape becomes. And at some point, you start to realize that the difficulty is not in your measuring tool. The difficulty is in the thing you are trying to measure. Continuous, curving, endlessly detailed reality does not naturally fit into neat, straight-edged boxes. That mismatch between the smooth complexity of the real world and the rigid simplicity of our measuring tools, that is the problem calculus was invented to solve. And the Egyptians and Babylonians were the first people we know of who felt that mismatch and tried to do something about it. But here is what is wild about the bigger picture. These two civilizations were not the end of the story. They were barely the beginning, because the instinct to pin down something continuous, something curving, something that changes moment by moment, kept appearing in China, in India, in Greece, in the Islamic world, in medieval Europe, over and over, in different centuries and on different continents. People kept bumping into the same fundamental challenge and kept inventing their own ways to wrestle with it. There is something deeply moving about that. I think the idea that this particular itch, this need to measure the unmeasurable, is somehow built into the human mind, that it was not one genius who woke up one morning and invented calculus. It was a slow, collective, species-wide groping toward an idea that was waiting to be found by anyone who stared hard enough at the right kind of problem. Across languages they did not share, in cities they had never heard of, using tools that looked nothing alike. People kept arriving at the same doorstep. They kept asking the same question. How do you capture something continuous with something discrete? How do you add up something infinite and get something finite? How do you measure a curve? And they kept finding pieces of the answer. One piece here, another piece there, never the whole thing, Never the unified vision that would eventually tie it all together, but always moving, always reaching, always getting a little closer. And all of these brilliant individual solutions, the Egyptian frustum formula, the Babylonian trapezoid method, the techniques that would later emerge in Greece and India and everywhere else, they all shared one limitation. Nobody had figured out that they were all examples of the same thing. Nobody had looked at the frustum problem and the Jupiter problem and the area of a circle problem and said, these are all the same idea, wearing different clothes. That realization, the one that would eventually turn a collection of clever tricks into an actual branch of mathematics, was still a very long way off. And the person who came closest in the ancient world was a man drawing shapes in the sand on the coast of Sicily. The thread of this idea, this instinct that you could pin down something exact by adding up something infinite, was about to travel west across the Mediterranean to a place called Syracuse, and into the hands of someone who would push it further than anyone had pushed it before. So those ideas, the ones Archimedes was chasing in Syracuse with his infinite cascade of triangles, they didn't stay in the Mediterranean. They didn't follow any map anyone had drawn. They traveled the way ideas always travel, which is to say, unpredictably, unevenly, and sometimes not at all. Sometimes an idea crosses an ocean on a trading ship. Sometimes it sits in a manuscript for 1,000 years waiting for someone to open it. And sometimes, most remarkably of all, it just shows up again, independently, on the other side of the world, in the mind of someone who has never heard of the person who had it first. That's the part of this story we're in now, the relay race. And the thing about this particular relay race is that the runners didn't always know each other existed. Let's start in China. Around the 3rd century of the Common Era, there's a mathematician named Liu Hui, and he's working on a problem that would have been very familiar to Archimedes if the two of them could have somehow met across the centuries. Liu Hui wants to know the area of a circle. He doesn't have calculus. He doesn't have algebra in the way we'd recognize it. What he has is geometry, patience, and a beautifully simple idea. Inscribe a polygon inside the circle, count the sides, calculate the area, then add more sides. A hexagon becomes a 12-sided polygon. 12 sides become 24. 24 become 48. And with each step, the polygon fits more snugly inside the circle, its edges creeping closer and closer to the actual curve. Liu Hui pushed this all the way to a polygon with 3,072 sides. And the area of that polygon was so close to the area of the circle that the difference was essentially invisible. He was doing the method of exhaustion. Same idea Archimedes used. Same deep intuition about approaching a value without ever quite arriving at it. But Liu Hui had never read Archimedes. As far as we can tell, he had no access to Greek mathematical texts. He arrived at this on his own, working in a completely different tradition, writing in a completely different language, separated by centuries and thousands of miles. Same idea, different continent, figured out from scratch. In that pattern, that independent rediscovery is going to keep showing up throughout this story. It's going to show up so often that by the end, you might start wondering whether these ideas were invented by people at all, or whether the people just happened to be the ones who noticed them. Now, let's move forward a few centuries and shift west to the Islamic world, because from roughly the 8th century to the 13th century, something extraordinary was happening in the cities of Baghdad, Cairo, Cordoba, and Samarkand. This period, often called the Islamic Golden Age, was one of the most productive intellectual eras in human history, and mathematics was at the center of it. The Abbasid Caliphate, centered in Baghdad, made a deliberate decision to preserve and translate the intellectual heritage of every civilization it encountered. Greek texts, Indian texts, Persian texts, all of it. They built the House of Wisdom in Baghdad, which was part library, part translation bureau, part research institute, and the scholars who worked there didn't just translate, they extended. They took the best ideas from every tradition and pushed them further. One of the figures who matters most for our story is Ibn al-Haytham, born around 965 inches Basra, in what is now Iraq. He eventually moved to Cairo, and the range of his work is staggering. He's most famous for his contributions to optics. He essentially pioneered the experimental method in the study of light, writing a treatise that influenced European science for centuries. But for our purposes, what matters is his mathematics. Ibn al-Haytham developed methods for computing sums of integers raised to the fourth power. Now, that might sound abstract, but here's why it matters. Computing sums of powers is exactly the kind of problem you run into when you're trying to find the area under a curve. It's integration, not the formal, systematic integration that Newton and Leibniz would later develop, but the raw material for it, the specific calculations you need when you're adding up the areas of thinner and thinner slices under a curve. Ibn al-Haytham was solving integration problems in 10th century Cairo. He didn't call it that. He didn't have the framework to see it as part of a general theory, but the mathematical substance was there, and he was centuries ahead of anything happening in Europe at the time. The Islamic world also gave us algebra itself. The word comes from al-Jabr, the title of a treatise by al-Khwarizmi, whose name gives us the word algorithm. They gave us the numeral system you and I use every day. They preserved Euclid, Archimedes, Apollonius. Without the translation movement of the Islamic Golden Age, most of ancient Greek mathematics would have been lost entirely. Europe would later build its mathematical revolution on texts that survived only because scholars in Baghdad and Cordoba thought they were worth saving. So that's China and the Islamic world, both making enormous contributions to the ideas that would eventually become calculus. But the most remarkable chapter of this relay race, the one that genuinely changed how I think about the history of mathematics, that comes from a place most Western history books barely mention. It comes from a small patch of land on the southwestern coast of India, a region called Kerala. And what happened there is From a modern perspective, nothing short of extraordinary. Let me tell you about a man named Madhava of Sangamagrama. Madhava was born around 1,340 inches, a town called Sangamagrama, near the modern city of Cochin in Kerala. We don't know much about his personal life. The historical record is thin, the way it often is for medieval Indian scholars who worked outside the major royal courts. What we know is what he did. And what he did was found what we now call the Kerala School of Astronomy and Mathematics, a lineage of scholars that would continue producing original mathematical work for over 200 years after his death. Madhava worked in relative isolation from the European mathematical tradition. Kerala was a trading hub, yes, connected to the wider world through the spice trade. But there's no evidence he had access to Greek mathematical texts or to the work coming out of the Islamic world. He was working from the Indian mathematical tradition, which had its own deep history going back to Aryabhata and Brahmagupta, and he was pushing it further than anyone had pushed it before. And what this man and his students figured out is, from a modern perspective, genuinely staggering. They developed infinite series expansions for the trigonometric functions sine, cosine, and arctangent. Let me make sure that lands properly, because it's easy to let a sentence like that slide past without feeling its weight. An infinite series is a way of expressing a number or a function as the sum of infinitely many terms, each one smaller than the last, that together converge on an exact value. It's one of the most powerful ideas in all of mathematics, and it's the foundation of everything from Taylor series to Fourier analysis to the way your phone computes a cosine. And here's an analogy that might help it click. Imagine you're stacking coins on a table. The first coin is an inch thick. The next one is half an inch. The one after that is a quarter of an inch, then an eighth, then a 16th. You keep going forever. Each coin half as thick as the one before it. Now, how tall is the stack? It never actually reaches 2 inches. No matter how many coins you add, there's always a tiny gap remaining. But the gap gets so impossibly small, so vanishingly thin, that 2 inches is the only honest answer. The stack converges to 2 inches. That's the idea behind an infinite series. You add up infinitely many terms, each one contributing less than the one before, and the total approaches a specific value with a precision that gets better and better forever. That's what Madhava was doing with trigonometric functions. He found that you could express the sine of an angle as an infinite series of terms, each one computed from the previous one by a specific rule. Same for cosine, same for arctangent. And the series for arctangent is particularly important because when you plug in the right value, it gives you pi. Madhava and his students computed pi to 11 decimal places using these series. 11 decimal places in the 1400s. To put that in perspective, most European mathematicians at the time were working with pi values accurate to maybe 3 or 4 decimal places. Madhava was centuries ahead, working with tools that wouldn't appear in European mathematics until the 1600s and 1700s. The Kerala school also developed what we'd now recognize as Taylor series expansions. The idea that you can represent a smooth function as an infinite polynomial, with each term capturing a finer and finer correction to the approximation. This is one of the cornerstones of modern calculus, and it's named after Brooke Taylor, who published it in 1715. Madhava and his students had equivalent formulations roughly 250 years earlier. I need you to sit with that for a moment. 250 years. A school of mathematicians in southern India, working in a tradition that most of the world has never heard of, arrived at ideas that we routinely credit to European mathematicians who came centuries later. And now here's the historical puzzle that people still argue about. One of the most fascinating, unresolved questions in the history of science. Did any of this knowledge travel to Europe? The chronology makes it possible. Kerala was a major hub of the spice trade. Portuguese ships arrived on the Malabar coast around 1500. Jesuit missionaries were active in the region and were known to collect local scientific and mathematical manuscripts. The trading routes were there. The contact was there. The timeline would allow it. But we've never found direct proof. No letter, no translation, no manuscript with a clear chain of custody from Kerala to Europe. As far as the documentary evidence goes, the Kerala school's achievements were essentially unknown outside of India until a British researcher named Charles Matthew Wish wrote about them in 1835, well after Newton and Leibniz had already transformed European mathematics. So the most likely story is that Europe and India independently arrived at many of the same ideas through completely separate paths, which is, when you stop and think about it, one of the most remarkable things in the entire history of human thought. And here's a question worth sitting with for a moment. If multiple civilizations on different continents, speaking different languages, with no contact between them, kept arriving at the same mathematical ideas, what does that tell you about the ideas themselves? Maybe these aren't inventions. Maybe they're discoveries. Maybe infinite series and the relationship between areas and rates of change and the strange behavior of functions as they approach limits. Maybe all of that was always there, written into the fabric of how the universe works, waiting quietly for someone to notice. The Babylonians noticed a piece of it. Archimedes noticed a bigger piece. Liu Hui noticed the same piece from the other side of the world. Ibn al-Haytham noticed another edge of it. Madhava and his students in Kerala found an enormous chunk of it, and each of them was reaching toward the same underlying structure, the same truth, from their own direction. There's something deeply comforting about that, if you let it settle. The idea that mathematical truth isn't fragile, isn't dependent on any one civilization getting lucky. It's patient, it waits, and it keeps being found over and over by anyone who looks carefully enough at the right problems. But then comes the question that always follows, and it's a fair one. If the Kerala school had infinite series, Taylor-like expansions, pi to 11 decimal places, and concepts that look an awful lot like derivatives, Why isn't Madhava the father of calculus? Why do we give that title to Newton and Leibniz? The answer is what Newton and Leibniz did that the Kerala school didn't. And the answer matters because it helps us understand what calculus actually is as opposed to what it's made of. The Kerala school had brilliant pieces. They had infinite series. They had ways of computing derivatives of trigonometric functions. They had convergence. They had remarkable computational tools. But they didn't connect differentiation and integration into a single unified system. They didn't discover the fundamental theorem of calculus, the recognition that finding slopes and finding areas are inverse operations of each other, two sides of the same coin, and they didn't develop a general notation, a symbolic language that would let you take these ideas and apply them to any problem, teach them to any student, and build an entire discipline on top of them. Think of it this way. Imagine you have a workshop full of beautifully crafted parts, gears, springs, levers, bearings, each one exquisite, each one functional, but no one has assembled the machine. The parts are all there, but the thing that makes them powerful, the way they fit together into a system that does work, that hasn't been built yet. That's what Newton and Leibniz did. They didn't just find more parts. They built the machine. They saw the connection between the parts. They created a language for describing how the parts fit together. And they gave the world a tool that could be taught, generalized, and applied to problems no one had even imagined yet. The mathematician Victor Katz put it well when he said the Kerala school was not able to combine many differing ideas under the two unifying themes of the derivative and the integral, show the connection between the two, and turn calculus into the great problem-solving tool we have today. That's the difference, and it's a real difference, but it shouldn't, and it doesn't erase the fact that a school of mathematicians in southern India independently developed some of the most profound mathematical tools in human history. The relay race of ideas is long, and every runner matters, even the ones who never got to see the finish line. And this is where the whole story starts to converge. By the early 1600s, Europe had absorbed Greek mathematics through Arabic translation. It had algebra thanks to the Islamic world. It had coordinate geometry thanks to René Descartes. It had the Hindu-Arabic numeral system, the decimal point, and a growing collection of techniques for finding areas, tangent, maxima, and minima. Everything was in place. The stage was fully set. All the raw material, gathered from civilizations stretching back thousands of years and spanning the entire globe, was sitting there, waiting to be assembled. All it needed was two people brilliant enough to see what no one else had seen. And by one of those wild coincidences that history occasionally produces, it got two of them at almost exactly the same time. But the people who would finally assemble all these pieces into a single working machine, they were about to do it under the strangest circumstances imaginable. One of them was a 22-year-old sitting at home during a plague. The other was a diplomat who got handed a reading list and told to catch up, and they would spend the rest of their lives fighting about it. And so here we are in the 1600s, and the table is set. All the raw ingredients for calculus are scattered across Europe like pieces of a puzzle that nobody has realized fit together yet. Descartes, working in France in the 1630s, had done something that sounds simple but was actually a revolution. He connected algebra to geometry. Before Descartes, these were separate worlds. You had shapes on one side, equations on the other, and no bridge between them. Descartes built the bridge. He said, take any curve and you can describe it as an equation. Take any equation and you can draw it as a curve. That grid you probably remember from school, the x-axis and the y-axis, is literally named after him, the Cartesian plane. And the reason this mattered for calculus is that suddenly, instead of doing everything with pure geometric reasoning the way Archimedes had to, you could translate a shape into algebra and work with the algebra instead. It was like being handed a new language that made hard conversations dramatically easier. Around the same time, Pierre de Fermat, yes, the same Fermat who would later leave that famously maddening note in the margin, was doing something remarkable. Born in 1601 inches, southern France, Fermat was technically a lawyer. Mathematics was his side obsession. But this side obsession produced methods for finding the maximum and minimum values of curves and for drawing tangent lines, the lines that just barely kiss a curve at a single point. He was also working on what we'd now recognize as integration. And here is the detail that matters. Fermat was doing both halves of what would become calculus, but he never connected the two. He never stepped back and said, wait, these are the same thing, running in opposite directions. Then there was Cavalieri, an Italian mathematician, who published the method of indivisibles in the 1630s. His idea was beautifully intuitive. Think of a flat area as being made up of infinitely many, infinitely thin lines stacked side by side. Think of a solid as infinitely many, infinitely thin slices. Add them all up and you get the area or the volume. This is conceptually exactly what integration does. And then there was Isaac Barrow, born in 1630, a professor at Cambridge, Newton's teacher and mentor. Barrow was the first person to explicitly state and prove the single most important connection in calculus, that finding the slope of a curve and finding the area under a curve are inverse operations. They undo each other. He proved it geometrically. He had it, but he didn't take the next step. He didn't turn it into a general method, a machine you could apply to any problem. He saw the connection, proved the connection, and then essentially moved on. The machine building would be left to two people who were, at that moment, still very young. Isaac Newton was born on Christmas Day, 1664, in Woolsthorpe, a small village in Lincolnshire, England. By most accounts, he was not a remarkable child. He ended up at Cambridge more or less because his mother finally pulled him off the farm. But once he arrived, something ignited He started reading Descartes, he started reading Barrow, and he began consuming mathematics with an intensity that would define the rest of his life. And then, in 1665, the plague arrived. Cambridge closed its doors. Students were sent home. Newton went back to Woolsthorpe, back to his mother's farm. And in the roughly 18 months that followed, what historians sometimes call the miracle years. He invented calculus. He discovered the laws of motion. He worked out the theory of universal gravitation. He laid the foundations for his work on optics. He was 22 years old. I need to pause on that because it's the kind of sentence that can just slide past if you're not paying attention. A 22-year-old sitting at home during a pandemic with no collaborators, no library beyond his own books, working essentially alone, produced foundational breakthroughs in 4 separate fields. Any one of those achievements would have been enough to make him one of the most important scientists in history. He did all of them in 18 months. That's not a career. That's a single stretch of solitude on a farm during a plague. It's almost unreasonable. Newton's approach to calculus was deeply physical. He called his system the method of fluxions. A fluxion was a rate of change, essentially what we now call a derivative. He thought of curves not as static shapes, but as paths traced by moving points. And he wanted to know how fast those points were moving at any given instant. His calculus was born from physics, from motion, from the question of how things change over time. He wrote it all up in 1666, and then he didn't publish it. He shared it privately with a small circle of mathematicians. Pieces showed up implicitly in his Principia Mathematica, published in 1687, one of the most important scientific books ever written. But he didn't formally publish his calculus until decades later. Some of it didn't appear in print until 1737, over 70 years after he'd worked it out. Imagine writing a letter that would change the world and then refusing to mail it for 70 years. Why? Newton was famously private and famously terrified of controversy. He'd gotten into nasty public disputes over his work on optics, and the experience had scarred him, so he held on to his most important mathematical work, sharing it in whispers. And that decision, that peculiar collision of genius and anxiety, is what set up everything that came next. Because, meanwhile, in Germany, someone else was heading toward the exact same destination from a completely different starting point. Gottfried Wilhelm Leibniz was born in 1646 Zoll, Leipzig. If Newton was a man who burrowed deep into physics with almost monastic focus, Leibniz was the opposite: philosopher, diplomat, logician, historian, lawyer, political advisor, and mathematician. He served as counselor to German courts, designed calculating machines, wrote extensively on metaphysics, and corresponded with practically every major intellectual in Europe. One of the most wide-ranging minds of his century, the kind of person who could attend a diplomatic dinner in the evening and spend the early hours of the morning working out a new theory of logic. Where Newton withdrew from the world, Leibniz threw himself into it. And he didn't start seriously studying mathematics until his mid-20s. In 1672, Leibniz traveled to Paris on a diplomatic mission and met the Dutch mathematician Christiaan Huygens. Huygens was one of the leading scientists in Europe, a man who had made important contributions to optics, mechanics, and probability. He looked at the ambitious young diplomat, recognized something, and essentially handed him a reading list. Catch up. Leibniz caught up astonishingly fast. His approach was fundamentally different from Newton's. Where Newton thought about motion and velocity, Leibniz was drawn to geometry, to tangent lines, to the tiny differences between nearby points on a curve. His building blocks were differentials, infinitely small changes in x and y. Where Newton saw the world flowing, Leibniz saw it built from infinitesimal pieces fitted together. Two men, different traditions, different problems, different frameworks, arriving at mathematically equivalent systems, like two people building the same bridge from opposite sides of a river, never seeing each other's work, and meeting perfectly in the middle. That doesn't happen because one person copied the other. That happens because the bridge was always there, waiting to be built. And there is something beautiful in that, something that says more about the nature of mathematics than it does about either man. But Leibniz did something that Newton didn't, and it might be the single most consequential difference between them. He thought deeply about notation. By October of 1675, he had written down the elongated S that we now use for integration. From the Latin word summa, he introduced d for differential, giving us dx and dy over dx for the derivative. This notation wasn't just convenient, it was revelatory. It made the relationships between concepts visible on the page. The notation doesn't just record the math, it teaches the math, it thinks for you. And that quality, the ability of good notation to make ideas almost self-explanatory, is something mathematicians have always valued but rarely achieved this perfectly. Leibniz published in 1684. The paper was notoriously dense, but it was public, and the mathematical community seized it. Two Swiss brothers, Jakob and Johann Bernoulli, based in Basel, became Leibniz's most passionate champions, extending his calculus and spreading it across the continent. And then Newton heard about it, and he was absolutely convinced that Leibniz had stolen his ideas. His reasoning was simple. I developed this first, I showed it to people, it shows up in my Principia. Leibniz came after me, therefore he must have gotten it from my work. Leibniz's response was equally firm. Look at my manuscripts, look at the dates, look at the completely different approach. I came at this through geometry and tangent lines. Newton came at it through physics and motion. These are different paths that happened to lead to the same place. The controversy escalated for years. Allies on both sides published accusations. The mathematical communities of England and continental Europe took sides, and the dispute turned personal and ugly. Be 1712. the Royal Society of London convened an official investigation. The committee concluded that Newton had priority. The report was presented as an objective inquiry, and here is the detail that turns this whole episode almost darkly comedic. The report was actually written by Newton himself. He was the president of the Royal Society at the time. The man being investigated essentially wrote the verdict. But here's what's easy to miss in all the drama. The fact that Newton and Leibniz, starting from completely different traditions, solving different problems, using different frameworks, arrived at equivalent results. That's not evidence of plagiarism. That's evidence that they were chasing the same deep truth. And the truth doesn't care who finds it first. It doesn't care about Royal Society investigations or bruised egos. It just sits there in the structure of the universe, patient, indifferent, waiting for whoever looks carefully enough to see it. Now, before we leave these two men, we need to talk about the idea that connects everything they built, because there is a single theorem at the heart of calculus, one that Barrow saw geometrically and that Newton and Leibniz each grasped in their own way. It's called the fundamental theorem of calculus. And here is the most important sentence in all of mathematics. Differentiation and integration are inverses of each other. Finding the slope of a curve and finding the area under a curve are opposite operations. They undo each other, like how addition undoes subtraction, like how opening a door undoes closing it. If you zoom into a curve and ask how steeply it's rising at one point, that's differentiation. If you ask how much total area has accumulated under the curve up to where you are now, that's integration. And these two questions, which seem like they should have nothing to do with each other, are secretly the same question asked in reverse. Just sit with that for a second, because it really is remarkable. Two operations that seem completely unrelated, one about slopes and one about areas, turn out to be mirror images of each other. What that means is extraordinary. It means the two halves of calculus, the half about rates of change and the half about accumulation, are not two separate subjects stitched together by coincidence. They are one subject, one idea, viewed from two directions. Barrow saw this. Newton and Leibniz turned it into a machine you could use on anything. They gave it notation, methods, and power. They turned a beautiful geometric insight into something a student could learn, a scientist could apply, and an engineer could build with. And now we come to the part of this story that carries the most emotional weight. Leibniz spent the last years of his life consumed by the priority dispute. The Royal Society's report, authored by his rival, had essentially labeled him a plagiarist. His patrons in Hanover grew cold. The Elector of Hanover had become King George I of England in 1714, and suddenly maintaining a friendly relationship with Newton's rival was politically inconvenient. The man who had served these courts faithfully for decades, who had written their legal briefs and conducted their diplomacy, was quietly pushed aside. Leibniz was left behind. He died on November 14, 1716 in Hanover, bitter, isolated, largely abandoned by the people and institutions he had served for most of his life. The controversy unresolved, his reputation, at least in England, still that of a thief. His funeral was small and unceremonious. One observer noted that he was buried like a highway robber. Almost no pomp, almost no recognition, as though the man being lowered into the ground had not reshaped the intellectual landscape of the world. Let that settle for a moment, and here is what happened next. And it might be the most striking piece of historical irony in all of science. The entire world learned calculus in Leibniz's language, not Newton's. Newton's notation, his system of dots above letters, survived in some corners of physics, but it was clunky, hard to extend, hard to generalize. Leibniz notation, the elongated S, the dx, the dy over dx, was elegant and intuitive and powerful. It made the structure of calculus visible. It could grow with the subject, and it won completely. Every calculus textbook you've ever seen, every physics equation on every blackboard in every university, every engineering formula, every piece of notation in machine learning and artificial intelligence, written in the language of the man who died thinking he had lost. Newton won the fight. Leibniz won the war, and he never knew it. I find something deeply moving about that. Not triumphant, not satisfying in the way you'd want it to be. Just human. The math doesn't care about priority disputes. The notation doesn't know who won the argument at the Royal Society. The elongated S doesn't carry a grudge. And dy over dx has no memory of the fight that nearly destroyed the man who created it. The work survives. The work speaks for itself. And sometimes, when human institutions fail and powerful men abuse their position, the only justice that arrives is the quiet kind, the kind that lives in the work itself, long after everyone who fought about it is gone. So by the early 1700s, the machine existed. Calculus had been born twice, unified by a theorem that connected its two halves. The Bernoulli brothers were already extending it, pushing it into new territory. The notation had been chosen by history. Calculus was real. It was public, and it was spreading across Europe like a new language. But there was a crack in the foundation, a logical crack so deep that a bishop would publicly humiliate the entire field of calculus. And it would take 150 years for anyone to fix it. Now, let's slow down for a moment, because up until this point, we've been telling you a story, a really good story, full of rivalries and stolen credit, and a man buried like a highway robber. But the machine itself, the thing Newton and Leibniz actually built, we haven't really opened it up and looked inside. So let's do that now. Let's get our hands on the machinery. And I promise you, the way it works is more elegant than you'd expect. We need to start with an idea that sounds simple, but turns out to be one of the most important ideas in all of mathematics. It's called a limit. And the best way to understand it is to imagine you're walking toward a door. Every step you take covers half the remaining distance. Your first step gets you halfway there. Your second step covers half of what's left. Your third, half again. You can keep doing this forever, and you will never actually reach the door. There's always a tiny gap. But, and this is the part that matters, you can get as close as you want. Want to be within 1 inch? You'll get there after enough steps. Within a millionth of an inch? Keep walking. You'll get there too. The door is your limit. You're approaching it endlessly, getting closer with every step, but you never arrive. And that's not a failure. That's the whole point. A limit isn't about reaching a destination. It's about proving that you can get as close as you want, no matter how absurdly close someone demands. That guarantee of closeness is what makes a limit powerful. And limits are the engine underneath everything in calculus. Every derivative, every integral, every series, all of it, built on this one quiet idea of approaching without arriving. So let's talk about derivatives. Imagine you're standing on the side of a road, watching a car drive past. Someone asks you, how fast is that car going right now? Not the average speed for the trip, not how fast it went over the last hour. Right now, at this exact instant, what does the speedometer read? That question is the question that launched calculus, because speed is distance divided by time. You measure how far something went, divide by how long it took, and you get a speed. But that gives you an average. What happens when you shrink that time interval all the way down over the last second? The car traveled some distance over the last tenth of a second, less over the last thousandth, even less if the interval is truly zero. You've got 0 divided by 0. That's nonsense. But if you watch what happens as the interval shrinks toward 0, if those averages settle toward a specific number, that number is your instantaneous speed. That number is the derivative. There's a geometric way to see this that I find even more satisfying. Picture a curve on a graph. Pick a point on that curve and pick another point nearby. Draw a straight line through both. That line is called a secant line, and its slope tells you the average rate of change between the 2 points. Now slide the second point closer. The line tilts, adjusts. As the gap between the 2 points shrinks to nothing, what you're left with is a tangent line, a line that touches the curve at exactly one place, with exactly the slope of the curve at that place. And here's what's quietly beautiful. If you zoom in on any smooth curve, really zoom in, it starts to look straight. It starts to look like its own tangent line. The derivative is what the curve looks like when you get so close that all you can see is one tiny straight piece. Local truth, what's happening right here, right now, at this exact point. Not the big picture, not the whole journey, just this one moment, captured with perfect precision. Now, computing derivatives from scratch using the limit process every time would be incredibly tedious. So people figured out shortcuts, rules that let you skip straight to the answer because the limit had already been done once and for all. The simplest is the power rule. If your function is x raised to some power, the derivative is that power multiplied by x raised to 1 less. So the derivative of x squared is 2x. The derivative of x cubed is 3x squared. You bring the exponent down and subtract 1. That's it. One rule covering an enormous range of functions. Then there's the product rule for when two functions are multiplied together. And then the chain rule, which is probably the most important rule in all of calculus. The chain rule handles composed functions, situations where one function is nested inside another. You differentiate the outer function, keep the inner function in place, and multiply by the derivative of the inner function. It sounds fiddly in words, but in practice it becomes almost automatic. And this single rule is what powers the training of every neural network on the planet right now. Every time an AI model learns from data, it's using the chain rule millions of times per second. A rule worked out in the late 1600s, running underneath every chatbot conversation, every AI-generated image, every recommendation algorithm. The fact that the 300-year-old calculus rule is the engine of modern artificial intelligence never stops being remarkable to me. But let me introduce you to someone who took all of these tools and ran with them so far that mathematics has never quite recovered. His name was Leonhard Euler, born in 1707 Zoll, Basel, Switzerland, the same city that produced the Bernoulli brothers. His father wanted him to become a pastor. Instead, Euler became the most prolific mathematician who has ever lived. His collected works fill over 90 volumes. He wrote on calculus, number theory, mechanics, optics, astronomy, music theory, fluid dynamics. He introduced the notation f of x for a function, gave us the Greek letter sigma for summation. He standardized so much of the mathematical language we use today that it's hard to talk about mathematics without speaking in a language he helped build. And then there's his story, which is the part that always gets me. In his late 20s, he lost vision in his right eye. He kept going. Decades later, a cataract took his left eye, nearly completely blind, and his output increased. He dictated papers from memory, composing complex arguments entirely in his head. On the day he died, in 1783, he spent the morning calculating the orbit of Uranus, had lunch with his family, and died that evening. The man spent his final morning on Earth doing calculus. Among Euler's thousands of results, one stands out as perhaps the most beautiful equation in all of mathematics. It connects 5 constants from completely different corners of the mathematical universe. The number E, roughly 2.718. The imaginary unit I, the square root of -1. Pi, the ratio of a circle's circumference to its diameter. The number 1. And 0. Euler showed that E raised to the power of I times pi plus 1 equals 0. 5 numbers, 5 pillars, one short equation. It emerges from the Taylor series of the exponential function applied to complex numbers, and It reveals something genuinely deep about the connection between growth, rotation, and geometry. Even if you don't follow all the details, the equation has a quality that's hard to describe. It feels too perfect to work, and yet it does, every time, without exception. Now, the Bernoulli brothers deserve their own space here. Jakob and Johann, both from Basel, were among the very first to seriously take up Leibniz's calculus and push it further. They also had one of the pettiest sibling rivalries in scientific history. They accused each other of stealing ideas, competed for the same prizes, and argued publicly for years. Johann once submitted a solution to a mathematics competition under a false name to avoid being associated with his brother. Beautiful mathematics, wrapped in a deeply unpleasant family dynamic. But the work they produced transcended the petty fights, the way it always seems to. And one of the problems from this period is the Brachistochrone. Johann Bernoulli posed it in 1696. The question is simple. A ball sits at a high point. A low point is some distance away. Gravity pulls the ball down. What shape of slide gets the ball from top to bottom in the shortest possible time? Your instinct says a straight line, shortest distance, fastest route, but the straight line isn't actually fastest. If the slide starts steep, the ball picks up speed quickly, and that extra speed can more than make up for the longer path. So the fastest slide is curved. But curved how? The answer is a cycloid. A cycloid is the curve traced by a point on the rim of a wheel as the wheel rolls along a flat surface. Picture a piece of gum stuck to a bicycle tire. As the tire rolls, the gum traces a graceful arc. That arc is the fastest possible path between 2 points under gravity, not a straight line, not a circular arc, a curve drawn by a rolling wheel. There's something deeply satisfying about that result. The way a practical question about speed and gravity resolves into this elegant geometric object that nobody expected. Newton also solved the problem, reportedly in a single evening. When Bernoulli saw the anonymous solution, he supposedly said, "I recognize the lion by his claw, but now I need to tell you about a crack in the foundation, because everything we've just discussed, limits, derivatives, the power rule, the chain rule, Euler's formula, the Brachistochrone, all of it was built during a period when the logical foundations of calculus were, to put it gently, a mess. Here's the problem. When Newton and Leibniz set up the derivative, they needed infinitesimals, infinitely small quantities, not zero, because you can't divide by zero, but smaller than any number you could name. They used these infinitesimals to set up ratios, cancel terms, derive results. Then at the end of the calculation, they treated the infinitesimal as if it were zero and threw it away. They needed it to not be zero at the beginning. Then they needed it to be zero at the end. A logical contradiction. And everybody knew it. And everybody kept using it because the answers came out right. And here's the part that I find genuinely wild. For 150 years, The greatest mathematicians in the world were using a tool that gave them correct answers through incorrect reasoning. They could predict the orbits of planets, the paths of cannonballs, the flow of heat through metal, all from a method that logically shouldn't have worked. It was like building a skyscraper and then discovering the blueprints had a mathematical error in the foundation. But the building is still standing. Every floor works. Every elevator runs. But the blueprints, if you look carefully, contain a step that makes no sense. It was like a spell that nobody could explain, but everybody could cast. In 1734, a bishop named George Berkeley decided to look carefully. Berkeley was born in 1685 inches, Ireland, a philosopher and theologian, not a mathematician, but he was sharp, and he noticed that mathematicians were using calculus to challenge religious arguments about faith. Berkeley thought this was rich, given that their own foundations were logically broken. So he wrote a pamphlet called The Analyst and tore into the structure of calculus with surgical precision. His most famous line is devastating. He called infinitesimals the ghosts of departed quantities. And honestly, he was right. The way infinitesimals were used was logically inconsistent. The answers were correct. The reasoning that produced them was not. The entire edifice was getting right answers through a process that was, strictly speaking, nonsense. And the mathematicians of the 18th century knew Berkeley had a point, even if they didn't want to admit it. They just couldn't figure out how to fix the problem without breaking everything that worked. It took over a century. The first person to seriously attempt the repair was Augustin Louis Cauchy, born in 1789 inches, Paris. Cauchy was brilliant and difficult, a royalist in an era of revolution, the kind of mathematician who produced incredible work at a ferocious pace while managing to alienate nearly everyone around him. In the 1820s, he began replacing infinitesimals with limits. Instead of a quantity that is infinitely small, Cauchy described a quantity that can be made as small as you like. Instead of a mysterious object, a transparent process. That shift changed everything. The second was Karl Weierstrass, born in 1815 inches, what is now northwestern Germany. Weierstrass spent years stuck teaching high school, doing mathematics on the side that nobody knew about, until a paper he published caught the attention of the mathematical world. He didn't get a university position until his 40s, but once he arrived, he finished what Cauchy started. Weierstrass gave us the epsilon delta definition of a limit, the version every serious mathematics student still learns. The idea is this: you pick how close you want the output to be to the limit. I show you how close the input needs to be to guarantee it. If I can always find that guarantee, no matter how demanding you are, then the limit exists. No infinitesimals, no ghosts, no quantities that are somehow both zero and not zero. Faith replaced with proof. And with that, the crack was sealed. The skyscraper finally had blueprints that matched the building. I think there's something deeply admirable about that whole arc. Mathematics had the honesty to look at its most powerful tool and say, this works, but we don't understand why, and that bothers us. Most fields would have shrugged. The answers are right. Who cares about the foundations? But mathematicians cared. Cauchy cared enough to start the rebuild. Weierstrass cared enough to finish it. And the result is that calculus today sits on foundations as solid as anything in human knowledge. But derivatives are only one half of calculus. There's another half, the mirror image, and it's the one that quietly runs the modern world. Every time you stream a song, get an MRI, or send a text message, you're using the other half. And it starts with a question that sounds almost paradoxical. How do you add up infinitely many, infinitely small things? So, how do you add up infinitely many, infinitely small things? That question sounds like it shouldn't have an answer. It sounds like a trick, like something a philosopher would argue about in a tavern and never resolve, but it does have an answer. And the answer is integration, the other half of calculus. And I'd argue it's the half that quietly runs more of your daily life than you probably realize. Let's start with the simplest possible version. Imagine it's raining. You put a bucket outside your door and go back inside. The rain doesn't fall at a constant rate. Sometimes it pours, sometimes it drizzles, sometimes it nearly stops. At any given moment, you could measure how fast the rain is falling, how many milliliters per minute are landing right now. That measurement, that rate, is a derivative. It tells you the speed of accumulation at one instant. But here's the question you actually care about when you go back outside an hour later. How much water is in the bucket? You don't want the rate. You want the total, everything that accumulated over the entire hour. All those changing rates added together into one final number. That's an integral, the total accumulation of a quantity that's been changing continuously over time. Derivatives ask, how fast is it changing right now? Integrals ask, how much has piled up altogether? Their mirror images, and the fact that these two operations are inverses of each other, that breaking apart and adding up are mathematically opposite, is the deepest insight in calculus. We talked about it in the last part, the fundamental theorem. Now we're going to live inside the adding up half and see what it can do. So how do you actually compute one of these things? The idea is ancient. Archimedes was slicing parabolas into triangles 2,000 years ago. But the modern, rigorous version comes from a German mathematician named Bernhard Riemann. Riemann was born in 1,826 inches, a small village in what is now northern Germany. He was shy, deeply religious, and chronically anxious about public speaking, which is sort of painfully relatable for a man who would reshape half of modern mathematics. He died at 39 of tuberculosis, far from home in Italy. In his short life, he produced work that mathematicians are still unpacking, including a hypothesis about prime numbers that carries $1 million prize and remains unsolved. But the thing that matters here is what he did with integration. His idea is beautifully simple. Say you have a curve on a graph and you want the area of the region beneath it between 2 points. You can't just measure it because the boundary is curved. So you approximate, slice the region into thin vertical strips. Each strip is roughly a rectangle. The height is whatever the function equals at that point. The width is some small fixed amount. Add up all the rectangles. That's an approximation. Now make the rectangles thinner, more of them. Better approximation, thinner still, even better. And then you do the thing calculus always does. You take the limit, let the width shrink toward zero. The number of rectangles grows toward infinity. And in that limit, the sum converges to the exact area under the curve. That's the Riemann integral. Thin slices, add them up, take the limit. The same idea Archimedes had, but now with a name, a formal definition, and a framework that works for virtually any continuous function. And once you have this, an enormous number of problems become solvable. Volume of a sphere, slice it into thin circular disks. Integrate length of a curve, slice it into tiny straight segments. Integrate total force of water pressure on a dam, slice the dam into horizontal strips at different depths. Integrate, the pattern is always the same. Slice, approximate, limit, exact answer. Computing integrals by hand requires some techniques. And I want to mention a few, not because you need to memorize them, but because each one reveals something about how integration works as a way of thinking. They're not tricks to survive an exam. They're strategies for specific kinds of puzzles. Integration by parts handles products of functions. Essentially, the product rule run backward. Substitution unravels nested functions. The chain rule in reverse. Partial fractions breaks complicated fractions into simpler pieces you can handle one at a time. Each exists because a specific mathematical structure keeps showing up in real problems. And each technique is the natural response to that structure. There's a category of integrals that seems like it shouldn't work at all. Improper integrals, where the region extends to infinity. And what's remarkable is that sometimes the answer is finite. Take 1 over x squared. Compute the area under that curve from 1 all the way out to infinity, stretching forever to the right. The answer is exactly 1 square unit of area from an infinite region. The curve drops off so fast that the total area remains bounded. This kind of result, an infinite region with a finite measure, is one of calculus's genuinely surprising moments. It tells you something counterintuitive about infinity, that not all infinite processes produce infinite results. Some infinities are tame enough to add up to something you can hold in your hand. Let me take a brief detour into series, because they connect deeply to integration and they have their own surprises. The harmonic series, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, and so on forever, diverges. The terms shrink towards zero, and yet the sum is infinite. It grows so slowly you'd need about 200 million terms before it even reaches 20. But it does eventually surpass any number you name. The terms going to zero is necessary for convergence, but it's not sufficient. Now alternate the signs. 1 minus 1/2 plus 1/3 minus 1/4. This one converges, and it converges to the natural logarithm of 2. And here's where a callback is in order, because this result was known to the Kerala school of mathematics in India centuries before European mathematicians encountered it. Madhava and his students, working on the southwestern coast of India in the 1400s, figured out infinite series for trigonometric functions and for pi hundreds of years before these results appeared in Europe. The fact that mathematicians on different continents, separated by centuries, arrived at the same results is one of those things that makes you feel like the ideas were somehow waiting to be found. Now, here's where I want to shift gears, because I want to tell you about someone whose work I find absolutely extraordinary, not because of what he set out to do, but because of what he accidentally unleashed. Joseph Fourier was born in 1768 Pouce, Auxerre, a small town in central France, orphaned by 9, raised by a local bishop who recognized his talent. He survived the French Revolution, was nearly executed, caught Napoleon's attention, served as governor in Egypt during Napoleon's campaign, and eventually settled into mathematics and physics. His life was a novel, but the thing that made him immortal was a specific, almost mundane problem he got obsessed with in the early 1800s. He wanted to understand how heat spreads through a metal bar. That's it. You heat one end, leave the other cold, and the temperature changes over time at each point along the bar. Fourier wanted an equation to describe that process, and in solving it, he discovered something that changed mathematics forever. He found that any function, virtually any shape you could draw, can be written as a sum of sine and cosine waves, different frequencies, different amplitudes, layered together. You could take a sharp, jagged zigzag, something that looks nothing like a smooth wave, and if you add up the right combination of sine waves, you reconstruct it exactly. When Fourier first presented this idea, prominent mathematicians didn't believe him. Lagrange, who reviewed the work, was openly skeptical. It took decades for the mathematical community to work out when and why the claim was correct, and the effort spawned entire new branches of mathematics. But here's what gets me every time about this story. Fourier wasn't trying to revolutionize anything. He was thinking about heat and metal. And in solving that one specific problem, he stumbled onto one of the most powerful ideas in the history of science. Let me walk you through the connections, because each one deserves a moment to breathe. Start with your ears. Sound waves hitting your eardrums right now are not pure tones. They're messy, overlapping vibrations, hundreds of frequencies jumbled into one complex pressure wave. And deep inside your inner ear is a spiral structure called the cochlea, lined with thousands of tiny hair cells that respond to different frequencies. The cochlea physically decomposes the incoming sound wave into its component frequencies, and your brain reads the pattern. That's why you can tell a violin from a piano playing the same note. Different overtones, different Fourier spectra. Your auditory system performs a real-time Fourier analysis of every sound you hear, without you ever being aware of it. A man in the early 1800s trying to figure out heat in a metal bar described the mathematics of how you hear. I genuinely find that one of the most beautiful cross-field connections in all of science. Now the phone in your pocket, every photo you've sent has been compressed using Fourier's idea. JPEG works by breaking an image into small blocks and expressing each block as a combination of cosine waves. The high-frequency components your eye can't distinguish get thrown away, making the file small enough to send. MP3 compression does the same for sound, decomposing music into frequencies, removing what you can't hear, compressing the rest. The song you streamed this morning was processed by an insight from the early 1800s before it reached your ears and MRI machines. The technology that lets doctors see inside your body uses Fourier transforms as its core mathematical tool. The machine applies magnetic gradients that encode spatial information as frequencies. Different locations in your body produce signals at slightly different frequencies. The machine collects those frequency encoded signals, runs a Fourier transform, and decodes them back into an image of your organs. Without Fourier's mathematics, there is no MRI. The machine that saves lives every day in every hospital on the planet runs on an idea that started with a question about warm metal. Just sit with that for a second. And then there's the invisible web that connects you to everyone. Wi-Fi, 4G, 5G. These systems use a technique called orthogonal frequency division multiplexing, which splits data into many smaller streams sent simultaneously on different frequencies, all separated and reassembled using Fourier transforms. Every text you send, every video call, every scroll through anything on your phone. Fourier analysis running in real time. Every wireless signal you send or receive uses Fourier analysis. Every photo you've ever sent uses a version of Fourier's idea. A man in the 1800s trying to understand how heat spreads through a metal bar accidentally laid the mathematical foundation for the entire digital world. That sentence is worth reading slowly, because I think it might be the most extraordinary example of unintended consequences in the entire history of science. Fourier wasn't building the future. He was solving one problem, and the tool he invented turned out to be universal. In 1965, two American scientists named James Cooley and John Tukey published an algorithm that made all of this practical. Computing a Fourier transform on a large dataset is slow. N squared operations for n data points for millions of data points. That's unworkable. What Cooley and Tukey discovered was a way to compute the exact same result in n times the logarithm of n operations. For a million data points, that's a speed up by a factor of roughly 50,000. Their algorithm, the fast Fourier transform, has been called one of the most important algorithms of the 20th century. It's a beautiful exploitation of symmetry that avoids redundant calculations by breaking a big problem into smaller, identical pieces. Without it, digital audio, image compression, wireless communication, and medical imaging would all be impractical at modern scales. Every phone call you make runs faster because of what two people figured out in 1965. I want to close this part with one more idea that ties everything together. Taylor series. Here's the premise. Say you know everything about a function at a single point. Its value, its slope, its curvature, how its curvature is changing, and all the higher derivatives, every one of them, all at that one point. Brooke Taylor, an English mathematician working in the early 1700s, showed that all that local information is enough to reconstruct the entire function. You build an infinite polynomial whose coefficients come from those derivatives, and it reproduces the original function exactly. Think about what that means for a moment. All the information about where a function goes, everywhere, is encoded in what it's doing right here. The local contains the global. It's like a seed that holds the blueprint for an entire tree. The seed sits in your palm, small and compact and seemingly simple, but the roots, the trunk, the branches, the canopy, all of it is already written inside. A Taylor series is the mathematical version of that. One point, interrogated deeply enough, tells you everything. And I think that's one of the most striking facts in all of mathematics. There's something deeply satisfying about how Taylor's idea connects back to Fourier's. Fourier showed that any function can be decomposed into waves. Taylor showed that any smooth function can be reconstructed from its derivatives at a single point. Both are saying, in different languages, that functions contain hidden structure, that what looks like one thing on a graph is actually a combination of simpler things stacked together. Both are ways of seeing the invisible architecture inside mathematical objects. But calculus doesn't stop at waves and integrals. There's a level above this, a level where you're not just finding the best number, you're finding the best function, where the question isn't what value minimizes this, but what shape minimizes this. And at that level, calculus stops being a tool and starts being a language. The language that nature itself seems to speak, and that phrase, the language that nature speaks, isn't poetic exaggeration. It's closer to a literal description than you might think, because once you have derivatives and integrals in your toolkit, once you understand that the world is made of quantities that change, and that calculus is the machinery for describing that change, something opens up, a door into the way the physical world actually operates. At every scale, in every direction, we've come a long way to get here. You and I, we started with Archimedes drawing triangles inside a curve in ancient Syracuse. We've traveled through Babylon and Kerala and plague-quarantined England. We've watched Taylor's series reveal the hidden architecture inside functions, and Fourier decompose the world into waves. We've learned what derivatives do and what integrals do, and if you've stayed with me this far, even drifting in and out, you already have the pieces. Now let's see what happens when you set them loose on the real world. And to do that, we need to talk about differential equations. The name sounds intimidating, but the idea is surprisingly natural. A differential equation is an equation that relates a quantity to its own rate of change. Instead of solving for a number like you do in algebra, You're solving for a function, the shape of a curve, the path of a moving object, the way a population grows over time. Here's a way to feel it. Imagine a bank account that earns interest, where the interest depends on how much money is already there. The more you have, the faster it grows. That relationship, the rate of change is proportional to the current amount, is a differential equation. And when you solve it, you get the exponential function, that smooth, ever steepening curve that starts slow and then rockets upward. And that same equation, that same mathematical pattern shows up in places you'd never expect. It describes population growth when resources are unlimited. Every generation produces offspring who produce more offspring. It describes radioactive decay, where unstable atoms break apart at a rate proportional to how many remain. It describes the way a hot cup of coffee cools down, losing heat fast at first and then more slowly as it approaches room temperature. And here's something I find genuinely remarkable. Archaeologists use exactly this equation every time they carbon date a bone or a piece of ancient wood. Carbon 14, a radioactive form of carbon, decays at a known rate. When an organism dies, the carbon 14 in its body starts ticking down according to that exponential decay equation. By measuring how much is left, you solve the equation backward to figure out when the organism died. That's it. That's carbon dating, a mathematical idea about rates of change applied to atoms, telling us about history tens of thousands of years old. The connections in this subject never stop being surprising. Now let's move to another family of differential equations that shows up even more universally. Imagine pulling a weight on a spring and letting go. The spring pulls it back. The weight overshoots. The spring pushes it the other way, back and forth, oscillating. The equation says that the acceleration is proportional to the displacement but in the opposite direction. And when you solve it, you get sine and cosine. This is the reason those wave functions show up everywhere in physics. Not because mathematicians decided they were important, because they're the solution to the universe's most basic oscillation equation. A pendulum swinging, a guitar string vibrating, alternating current in a wire, atoms jiggling in a crystal, all solving the same equation at different scales. There's something deeply beautiful about that kind of unity, and it keeps going. The heat equation describes how temperature diffuses through a material. Put a hot spoon into a cold bowl of soup, and the heat doesn't teleport. It spreads outward gradually, and the rate of spreading depends on the temperature differences at each point. That diffusion is a differential equation. The wave equation describes how sound and light and ripples propagate through a medium, Maxwell's equations, the four equations governing all of electromagnetism, are differential equations. When James Clerk Maxwell solved them in the 1860s, they predicted electromagnetic waves traveling at a specific speed, and that speed turned out to be exactly the speed of light. He discovered that light is an electromagnetic wave by solving a differential equation. Just stop and hold that for a moment. A person sitting down with equations about electric and magnetic fields doing the math, and finding light on the other end. That's the kind of thing this language can do. In quantum mechanics, the Schrödinger equation governs how a particle's quantum state evolves. In fluid dynamics, the Navier-Stokes equations describe how liquids and gases move. We've had the Navier-Stokes equations since the 1800s, and we still can't fully solve them. For certain flows, we don't know whether the equations always produce smooth solutions or might sometimes blow up into infinite velocities from perfectly reasonable starting conditions. There's $1 million Millennium Prize waiting for whoever figures it out. 2 centuries of work, and the equations describing water in a pipe are still, in a fundamental mathematical sense, not fully understood. I find that both humbling and kind of thrilling. Now, let's shift gears. Everything so far has been calculus in one variable, but the real world doesn't work like that. Temperature depends on where you are and when. The height of a mountain depends on your east-west and north-south position simultaneously. When you have a function of multiple variables, you need multivariable calculus. The central idea is the partial derivative. You ask how fast the function changes if you move in one direction while holding everything else constant. Collect all those partial derivatives together and you get the gradient, a vector pointing in the direction of steepest increase. Picture a hilly landscape. The gradient at your feet points uphill. Pour water on the ground and it flows the opposite way, downhill, in the direction of the negative gradient. That image, water flowing downhill on a landscape, is one of the most important pictures in all of modern computer science, because this is exactly how machine learning works. When people talk about neural networks and deep learning, the conversation is usually about data and computing power, and those things matter enormously. But underneath all of it is calculus. Without calculus, neural networks cannot learn. Full stop. Here's why. A neural network is, at its most basic level, a machine with millions of tiny adjustable knobs. Each knob is a number called a weight. Feed the network an input, say a picture of a cat, and it runs that input through layers of calculations involving all those knobs and produces a guess. At first, before the network has learned anything, the knobs are random and the guesses are terrible. A cat might come back labeled submarine. The question is, how do you adjust millions of knobs so the guesses get better? You define a loss function, a single number measuring how wrong the guess is. That loss depends on all the millions of knobs, a function in a space with millions of dimensions. You want to find the valley, the combination of settings where the loss is smallest. So you compute the gradient. The gradient tells you for every single knob which direction to turn it to make the loss decrease. You nudge them all a tiny amount in that direction. The loss shrinks a little. The guesses get a little better. Repeat millions of times. And gradually, step by step, the network learns to recognize cats, translate languages, generate images and text and music, all of it powered by walking downhill on a lost landscape. That's gradient descent. That's multivariable calculus. And the engine that makes it work for deep networks is the chain rule. Remember the chain rule from earlier? The rule for differentiating composed functions. The derivative of the outer function times the derivative of the inner in a network with many layers. The output is a composition of functions stacked on top of each other, layer after layer. To compute the gradient through all those layers, you apply the chain rule backward from output to input. This process is called backpropagation, and it was formalized in a landmark 1986 paper by David Rumelhart, Jeffrey Hinton, and Ronald Williams. Hinton would go on to become one of the most influential figures in the entire history of artificial intelligence, sometimes called the godfather of deep learning. And the mathematical heart of his contribution is a rule that Leibniz figured out in the 1670s. Hold that thought for a second, because the span of it is worth feeling. Leibniz, sitting in Paris 300 years ago, working out the notation for differentials, could not have imagined a neural network. He had no concept of a computer. But the chain rule he discovered is the same chain rule that, 3 centuries later, makes it possible for a machine to look at a photograph and tell you what's in it. The math didn't change. The application changed. The idea persisted. Now there's one more branch I want to touch on before we reach the end. The calculus of variations. Regular calculus asks, what number minimizes a function? The calculus of variations asks what function minimizes a quantity, not the best point on a curve, the best curve itself. Imagine 2 points, one high and one low, and you want a ramp between them, so a ball rolling under gravity arrives at the bottom in the shortest time. A straight line isn't the fastest path because the ball needs to pick up speed early. The actual fastest curve is called a brachistochrone, and it's a cycloid, the shape traced by a point on a rolling wheel. Johann Bernoulli posed this problem in 1696, and Newton solved it in a single evening, reportedly annoyed at being interrupted. But the implications reach far beyond rolling balls. Soap films find the shape that minimizes surface area. The hanging chain makes the curve that minimizes energy. Light bends at boundaries along the path that minimizes travel time. Joseph Louis Lagrange, born in Turin in 1736, took this further than anyone. He reformulated all of mechanics using a single principle. The path a physical system actually takes is the one that extremizes a quantity called the action, an integral of the Lagrangian, the physical world. In Lagrange formulation, is solving an optimization problem at every moment. William Rowan Hamilton, born in Dublin in 1805, who was reading Latin, Greek, and Hebrew by the age of 5, took Lagrange's ideas deeper still, revealing a geometric structure that would later turn out to be exactly the right language for quantum mechanics. And that brings us to Richard Feynman, born in New York in 1918. Feynman was one of the most brilliantly original physicists of the 20th century. He had this extraordinary ability to see through layers of mathematical formalism to the physical picture underneath, and then find new mathematics that matched the picture better than anything before. And his path, integral formulation of quantum mechanics, took the calculus of variations somewhere no one had expected it could go. In classical mechanics, a particle takes one path, the one that extremizes the action. The universe, in Lagrange's picture, picks the optimal route. But in Feynman's quantum mechanics, the universe doesn't pick. A particle takes every possible path, every conceivable trajectory between 2 points contributes to the outcome. Some paths are straight and sensible, some loop around backward, some zigzag through space in ways that seem absurd. And the probability of the particle going from here to there is calculated by summing up contributions from all of these paths. An integral over the entire space of possible trajectories. The classical path, the sensible one, emerges because contributions from paths near it reinforce each other, while contributions from wild, erratic paths tend to cancel out. But they all participate. They all matter. I want to be honest here. This is one of those places where the physics gets genuinely strange, where intuition gets slippery, and where a full accounting requires tools beyond what we can cover tonight. But the central image, a particle exploring every possible route and the universe somehow adding them all up, that image is real. It's not a metaphor. It's how the calculations are actually done. And those calculations produce predictions that match experiment to astonishing precision. Whatever is going on, this description works, and it's built from the ground up on integration, on adding up infinitely many contributions, the same idea that Archimedes was reaching for, drawing triangles inside a curve in ancient Syracuse. And here's what I want to leave you with. We started in Syracuse about 300 years ago. We traveled to Egypt and Babylon, where scribes computed volumes and tracked planets. We passed through Kerala, where Madhava worked out infinite series centuries before Europe. We sat with Newton in a plague-quarantined farmhouse. We followed Leibniz inventing notation the world still uses. We watched Euler and Fourier and Riemann build higher and higher, and we ended up here, inside the systems reshaping the world you live in. Systems that learn by walking downhill on a landscape of calculus. And through all of it, the same idea kept showing up. The idea that you can understand something exactly by approaching it from an infinite number of almost right answers, that the universe is continuous, that it changes smoothly, and that the language for describing that change, limits, derivatives, integrals, is not something humans invented out of nothing. It's something we've found over and over on different continents, in different centuries, as if the idea was woven into the fabric of things, waiting for someone patient enough to notice. After tonight, you might start to see it, the curve of a hill, the way your car accelerates from a stoplight. That's a derivative, the way sound fades as someone walks away. That's a function whose rate of change calculus describes the arc of a thrown ball, the spread of warmth from a radiator, the rhythm of your own breathing, a gentle oscillation governed by the same equation that describes springs and pendulums and vibrating atoms. That's all calculus. It was always calculus. You just didn't have the words for it yet. And Archimedes would not recognize a neural network. He wouldn't know what a computer is. But the mathematics he was doing, the art of approaching something exact by getting infinitely close, is there in every gradient descent step, in every backpropagation pass, in every generated image. 23 centuries later, his idea is still the engine. Change is all there is. Nothing in the universe is static. Your body is replacing its cells. The earth is spinning. Light is propagating. Stars are being born and scattering their elements across space. And calculus, this thing that started with a man drawing triangles inside a curved tube 300 years ago, is the language we developed to describe all of it. Not because we chose to, because the universe gave us no other option. And that's more than enough to carry into sleep. The math will still be there in the morning. It's been there for 300 years. It's not going anywhere. Calculus is the language of everything that moves, and everything moves